Welcome back. In the last lecture, we considered an AC circuit with purely capacitive load. In the lecture before that, we had talked about a circuit with a purely inductive load. So let us quickly summarize what we have learned so far. So what we found is this: if you take a purely resistive load, then you find that the current is in phase with the applied voltage. So the direction of the current in more complicated circuit becomes the reference direction with respect to which we talk about whether something leads or something lags. We'll see that when we take towards the end of today's lecture more complicated combinations of resistors, inductors and capacitors. What we found is that for an inductive load, so that is a circuit consisting of an inductance and a voltage, we found that the current lags behind the applied voltage. What is meant by current lagging behind is that if you look at a trigonometric variation, let's suppose a sine function or a cosine function for the voltage, then the corresponding expression for the current will be the same trigonometric function but with a phase which will lags means be negative. So something like if voltage is varying as cosine or sine of omega t, then the current will go as cosine or sine of omega t minus phi. The reverse situation happens for a capacitive load, and here the current leads the voltage. In other words, the phase of the current is ahead of the phase of the voltage, and so therefore if you are looking at a purely capacitive circuit, the current would become maximum before the voltage does. So this thing about what leads, what lags, it confuses people quite a bit. So the electrical engineers have a mnemonics for that, and that is written as Ellie the Iceman. Now this tells you that for an inductive circuit, which is what this L stands for, the EMF, that is the voltage, that leads the current. So E is for voltage and I is for current. And for the capacitive circuit, the current that is given by I, it leads the EMF or the voltage given by E. So what comes first is what is seen in this mnemonics. In both these or all the three circuits, the ratio of the voltage max to current max is given as follows. So if I have a purely resistive circuit, my current maximum, which I represent by Im, is given by Vm divided by R. R is of course the resistance in ohms. For an inductive load, we define an inductive reactance represented by XL, which is equal to omega times L, and this, in terms of this, my current is given by voltage maximum divided by XL. And for a capacitive load, we define a capacitive reactance by Xc, which is equal to 1 over omega C, and once again I have my Im as equal to Vm divided by Xc. So this is, here it is equal to Vm divided by omega L, and here it is Vm times omega times C. You realize that there is a difference in the way the frequency or the angular frequency omega comes into these expressions. In all these cases, the trigonometric variations that we talk about are the following. Let V of t be Vm sin omega t, and let me take the current I of t as Im sin omega t plus phi. Here phi is the amount by which the current leads the voltage. In this, with this notation, if I have a purely resistive circuit, then of course phi is equal to 0, which implies that current and voltages are in phase. For an inductive circuit, as we have seen, current lags the voltage by pi by 2, in which case phi must be equal to minus pi by 2, because I have taken the current expression to be omega t plus phi. And for capacitive circuits, the current leads the voltage by pi by 2, so therefore phi will be equal to pi by 2. I have mentioned earlier, though we will not really be using it, when it comes to complicated circuits, it becomes clumsy to deal with different types of trigonometric variations for voltage, current, and things like that. So in electrical engineering, what is done for making the algebra simple is to take for voltage an exponential form. This is just a short introduction I am giving in next 5 minutes. If you find it little difficult, you just ignore it, because I will not be really using it as I go ahead. So what is done is the following. Supposing we take V of t instead of Vm sin omega t, I take Vm e to the power I omega t. Now remember that the exponential e to the power I omega t is cos omega t plus I sin omega t. As you notice that this really doesn't represent a physical situation, but mathematically the function that you want, which is V of t sin of omega t, is nothing but the imaginary part of this function. Similarly, if you wanted V of t to be Vm cosine of omega t, then it would be represented by the real part of this function. The reason for taking Vm e to the power I omega t instead of the cosine or the sine, mathematically exponential functions are much easier to deal with than trigonometric functions. And in that case, what we'll do is we'll carry on with the calculations, assuming the exponential functions, and then of course we'll At the end, we'll say we need to take the real part or the imaginary part, as the case may be. Now, if you do that, then the corresponding I of t would be given by Im e to the power I omega t plus phi. So once again, if we had taken V of t equal to Vm sin omega t, the corresponding current would be given by the imaginary part of this. Now notice the simplification in the algebra. The complex impedance, which would now be defined as V of t by I of t, is given by Vm by Im into e to the power minus I phi, because of the way we have taken this. And we had seen that for resistive circuits, phi was equal to 0. Which tells me that Z is nothing but Vm by Im. For resistive circuit, it is just equal to I. For an inductive circuit, phi was equal to minus pi by 2. So, and we have seen that Z is then Vm by Im, which is omega L times e to the power minus I pi by 2. Well, minus, but phi itself is minus, so e to the power plus I pi by 2, and that's equal to I omega L. Likewise, for a capacitive circuit, we have seen that Vm by Im is 1 over omega c, but this time it is e to the power minus I pi by 2. So therefore, this quantity is e to the power minus I pi by 2. So this is just equal to minus I 1 over omega c. Alternatively, it's also written as 1 over I omega c. So if I have R, L and C, all of them in series in a circuit, then I define my complex impedance as Z equal to R plus I times omega L minus 1 over omega c, and as per our notation for the complex reactance, so this is plus I times XL minus XC. Now you can see that this gives modulus of Z equal to square root of R square plus XL minus XC whole square, which is the same as XC minus XL whole square. And this is what we have been using all throughout. The phase of the complex Z, which is phi, is given by tangent of phi equal to XC minus XL divided by R. Now these relations can be shown in an impedance diagram, which looks like this, that it's a right angle triangle with one side being modulus of XC minus XL, this being resistance R, and naturally the hypotenuse is modulus of Z, as we have shown here. Let me look at what happened to power in such circuits. Now, what we said is that when we had a purely resistive situation, then the average rate at which it dissipates power, average power. So average for a resistive circuit was Im square R by 2. This came because I square R is the instantaneous dissipation of power, and if you take the form of current to be a sine function, then the I square will have a sine square, and over a period thus we have seen that the sine square or the cosine square function gives me the factor of half. So what is done is, in order to make this formula look similar to the way it looks for DC circuit, we define what is known as an RMS current. We could also define RMS voltage that way. So RMS current was simply Im divided by square root of 2, which we represent as I RMS. With this formula becomes identical to I RMS square R, which resembles the form I square R for a DC circuit. Now, this is the only element which actually dissipates power. Both capacitive and inductive circuits absorb energy in one part of the cycle and return the same to the source in another part. So the average power for both inductors and capacitors is equal to 0. So with this, let me now go over to a discussion of what happens to an LCR circuit when an alternating voltage is applied. So let's draw this is my voltage, which as before I will take it as Vm sine omega t. I have a resistance R, an inductance L, and a capacitance C. And so we will be interested in the next part of the lecture in discussing the properties of an LCR circuit in the presence of an alternating voltage. So look at this. I use still the same Kirchhoff's law, and I said that whatever voltage is supplied by the source is dropped through R, which I know is IR, through L, which I know is L di by dt, and through the capacitor, which I know is Q by C. So therefore, my Kirchhoff's law tells me that Vt minus Vr is the drop across the resistor, minus VL, the drop across the inductance, minus Vc is equal to 0. Alternatively, my V of t is equal to IR, this is for R, plus L di by dt, which is the back EMF expression that you remember, and plus Q over C. We will return to a formal solution of this problem little later in this lecture, but let us look at what statements I can make about this circuit. Let's look at this situation and let's see what statements I can make about it. Now, one thing you realize is this, that since this element R, L and C, they are in series, this is series LCR circuit. We may have different other form of LCR, So let me also write down here series LCR. So since they are in series, there can be a unique current through this entire thing. So the current must be unique. Through the three elements. In other words, the current that we are talking about should also have a fixed magnitude and a fixed phase difference with respect to this omega. So let me take for the current in the circuit I to be equal to Im sine omega t plus phi. I have not made any statement on what phi is for the simple reason I have three components behaving in three different ways in my circuits when they were acting alone. For resistor, the phi was 0. For inductance, it was negative. For capacitance, it was positive. So at this moment, all that I have said is the phi is 0. Now, source voltage is V equal to Vm sin omega. These are the two things that we know. Now, what I will do is this. I will first try to solve this problem or try to understand the implications of what we have said in a graphical manner. So let us do that. We'll do the formal analysis a little later, but we'll see that a lot of it can be done by application of the graphical technique. So as before, I take the x-axis as my reference line. So this is t equal to 0 reference. And what we have said is this, that at a time t, because this phasor is rotating with an angular velocity omega. So therefore, at time t, the phasor for the voltage which was initially aligned along the t equal to 0, the x-axis, points in a direction which makes an angle with the x-axis, the angle omega t with the x-axis. So let us draw this. This is omega t. Now, what we have taken is that the current to lead the voltage by an amount phi. So therefore, in this picture, my current would be, let me use a slightly different color. My current would be along this direction. So this angle is phi. And this is of course Vm. And this is because we have taken I to be given by Im sine omega t plus phi. Now what we want to do is this. We will try to, or we will be drawing the voltage phasors across the three elements, namely the resistance, the capacitance and the inductance. Now remember that the VR, that is the resistance between the voltage across the resistance, is along the current direction, because we have seen that a resistive circuit is in phase with current. So therefore, Im times R, so let me not generally take it here, that will help me in completing this. So this end of this red arrow is my Im times R. Now since I know that the inductive voltage it leads the current. Remember that in case of an inductor, the current lags, which is another way of saying the inductive voltage leads the current by pi by 2. So this would be the direction in which the inductive voltage will be. So this is VL, and correspondingly the capacitive voltage would be in the reverse direction. So this is VCM. Since VLM and VCM are oppositely directed, so there will be along VCM where the capacitive reactance is larger than the inductive reactance. So you subtract the two and put it somewhere here. Now this Vm that we have drawn, then if you complete this rectangle here or parallelogram here, so this amount from O to whatever, let's say A, so OA magnitude is XC minus XL times current. So this tells me, this graphical construction tells me that Vm square is Vm resistance square plus VCM minus VLM square, and that is equal to, this is Im times R whole square, and this is Im XC minus XL whole square. And so therefore my Vm is given by Im times square root of R square plus Xc minus XL whole square, which is nothing but Im times Z, where Z is the quantity which is within the square root. So this is R square plus Xc minus XL whole square. Now remember, when I was discussing the complex nature of the impedance, I had said Z is R plus I times Xc minus XL. I am not really going to be doing it. So far as I am concerned, I am only interested in magnitude of that quantity, and which obviously is R square plus Xc minus XL whole square. So this is the impedance that I look at. So repeating once again, the impedance consists of, so that is Z, it has a factor which is R, and it has Xc and XL. In a vector diagram, the resistance and these reactances, they are perpendicular, and Xc and XL themselves are oppositely aligned in the vector diagram. So this is the reason why I repeat, Z is given by square root of R square plus Xc minus XL whole square, where Xc as before is 1 over omega c and XL is omega L. Let me continue with my graphical analysis for a little longer by giving you examples. So let me consider an example, numerical example. So let me consider an LCR circuit. Supposing this is a 80 ohm resistance, I have a 0.1 Henry inductance, and a 25 microfarad capacitance. The source is, well, I'll just give you the frequency of the source, which I will conveniently take it as 400 radians per second. Omega is, let me sort of point out that 400 radians per second I am taking purely for calculation of ease. 60 hertz, which is reasonably common in US, corresponds to 377 ohms. Yes, 377 radian per second. But 400 is close enough so that we can take it as a reasonably physical number. So let us first make the following thing. Suppose I say that an RMS current of 2 amperes is passing through the circuit. Now we need to first find out various quantities, and we would be interested in knowing that if this is the situation, what is my voltage like, the source voltage like. But before that, let's calculate various things. R is of course very simple, that's given to be 80 ohms. Let's calculate the reactances. So Xc is equal to 1 over omega c. Both Xc and XL, they have the dimensions which are the same as that of ohms resistance. So I have taken omega conveniently to be 400. This is 25 microfarad. So 25 into 10 to the power minus 6. So that is 10 to the power minus 4 in the denominator. And so that takes me up there. And that is 100 ohms. And XL, which is just omega L. Omega is 400. L is 0.1. So that's equal to 40 ohms. Let me find out what is the total impedance like. So impedance, I repeat, is R square plus Xc minus XL whole square. So this is equal to 80 square plus 100 minus 40, that is 60 square. So that is just equal to 100 ohms. So therefore, my RMS voltage is given by RMS current multiplied by Z. RMS current is given to be 2 amperes, Z is 100, so it is 200 volts RMS. The peak will of course be square root of 2 times bigger. But let us take this opportunity of finding out what are the individual voltage drops. So resistance drop is just I times R, which is 2 into 80, that's equal to 160 volts. But remember, all these are RMS voltage. If you want peak, you have to multiply by square root of 2. The capacitive voltage, that is voltage drop across the capacitor, is 2, that is the current, times Xc. We calculated the Xc to be 100, so this is equal to 200 volt RMS, and VL, that is the voltage drop across the inductor, which is 2 times XL, and we calculated XL to be 40, so therefore 40 into 2, so it is 80 volt RMS. Now you can check that the source voltage, RMS source voltage, also satisfies the law of addition of vectors. So you can see that 200 square, that's V RMS square, that's given by VR square, which is 160 square, plus VC minus VL, so 200 minus 80 square. You can check. This is 160 square, this is 120 square, and that exactly works out to 200 square. Let's look at the phase. So, return back to the diagram. In doing these types of problem, you have to realize, if I am plotting a voltage, the statement that we have made, that for an inductive circuit the current lags the voltage, implies that for an inductive circuit voltage leads the current. So therefore, when you draw, you have to draw it keeping this in mind. So let's look at that. So let's suppose first I am trying to draw a vector diagram. So let me draw the current direction along the x-axis. That's also the direction in which the resistance drop takes place. So this is, let's take this is VR, and we just now calculated that my VR was 160 volt RMS. So this is 160. Now, so let me write it down here. VR is 160. These are all RMS values. VL was 80 and VC was 200 volts. So let's draw it here. So the VL, because it's inductor, it leads the corresponding voltage for the resistor. I repeat again, the voltage leads the current for an inductive circuit. The current lags, but voltage leads. So let's take the same scale and put some 80 here. So this is my VL. And since VC is 200, in terms of length it would be slightly bigger. So let's do that. So this is VC, which is 200 volts. So what we now do is this, that we find out what is VC minus VL. So all that we need is to chop off here by an amount 80. So this is VC minus VL. And if I am drawing the parallelogram here, then so this quantity is 200 minus 80, which is 160. Sorry, 120. So this is 120, this is 160, and the result is obviously this. So this is my Vmax for the source. Let me just put S there to indicate source. And we have seen that 120 square plus 160 square is 200 square. So therefore the length of this is 200. It is just accidental that this 200 and that 200 happens to be the same number. But look at this phase here. This is the amplifier. So notice the resultant voltage is lagging behind the current. Okay. So resulting voltage, that is the supply voltage, lags by phi. And how much is phi? You can immediately calculate. Phi is tan phi is 120 by 160, which is equal to 3 by 4. And if you look up your trigonometric tables, you will find this is 37 degrees or 0.64 radians. So this is the angle by which this is the phase lag of the total voltage with respect to the current or with respect to the resistive load. Now, incidentally, this situation that the net supply voltage lags behind the current happened because the capacitive reactance is larger than the inductive reactance. So as a result, this circuit is primarily, or let's say predominantly, a capacitive circuit. This circuit is predominantly capacitive in nature, hence voltage lags current. And the reverse would be true, which we will also show you by taking some other example. If you had taken a situation where the inductive reactance is bigger than the capacitive reactance. Now look at this. What does it actually mean? What does this phase signify? Now, this is telling you that there is a time lag between the time the current maximum occurs or the voltage maximum. Now, look at what we have said. We have said that my current is Im omega t plus phi, and the voltage maximum occurs at omega t equal to pi by 2, whereas current maximum occurs when omega t plus phi is equal to pi by 2. So therefore, there is a time lag. So time lag between current maximum and voltage max. This is done by observing that I max occurs when omega t plus phi is equal to pi by 2. The voltage max occurs when omega t is equal to pi by 2 because it's just a sine omega t. So therefore, the time lag is given by phi by omega is equal to, now we have said, now you have to be careful, this phi must be in radian. So this was 0.64 radian divided by omega, which is 400 radians per second, which is equal to 1.6 milliseconds. Now, one of the things that I would like to point out is for you to observe what happens when omega increases. That is, what is the situation with higher frequencies? You see, what happens if your omega increases, then this phi, which we had worked out, is tan of phi is given by xc minus xl divided by r. And so if omega increases, let's suppose I'm talking about a capacitor. Now, in that case, my phi would go to 0 for a capacitor. And the reason is very simple. We had said that my tan phi is xc minus xl divided by r, and if I have a dominantly capacitive circuit or just a capacitor, let's say, then xc is 1 over omega c. So when omega becomes large, my phi becomes 0. So what does it actually mean? It means that a capacitor will essentially behave like a conductor. So high frequency current will simply pass through. The reverse situation happens when omega approaches 0. That is, the circuit is resembling now a DC circuit, in which case the capacitor becomes like an open circuit, that is, no current passes. Now, that is of course obviously something which we already know. Now, remember that for an inductive circuit, the current magnitude so here what we said is capacitor behaves like a conductor. For an inductive circuit, on the other hand, the current magnitude is proportional to 1 over omega L. Exactly the reverse occurs because as omega increases, the circuit essentially behaves like an open circuit. So, for high frequency, and of course, reverse is true if you have essentially a DC passing through. Now, in this LCR circuit that we have talked about, which we calculated various things, what is the average power delivered? Now, remember that the only element of an LCR circuit which dissipates power is the resistive element, because on an average the capacitor and the inductor do not dissipate power, they absorb and release. So, average power is simply I RMS square times R. We have actually calculated already I RMS, or rather I RMS has been given to be equal to 2. So, this is 4R. So, 4 into 80 equal to 320 watts. As another example, let me take an RC circuit. This is an RC circuit with an alternating voltage. Let me take numbers. R is equal to 3 ohms, C is equal to 2.5 into 10 to the power minus 4 farad, which is 250 microfarad. Let's take omega somewhat high frequency, 1000 radians per second. And let's also take the supply voltage, V max is equal to 5 volts. Now, since it's an RC circuit, the current would lead the voltage. Only thing, the difference that occurs in all these is that if I had a purely resistive circuit, the voltage and the current would be in phase. Now, if you had a purely capacitive circuit, the current would lead by 90 degrees. If you have a combination, the current would still lead, but not by pi by 2. Now, let's see how it works. So, we said let V be 5 sin omega t. This is what is given. This is for the source. The current, I will take the general expression as Im sin omega t plus phi. I expect phi to be positive for the simple reason that current leads the voltage. How much? I don't know. Had it been a purely capacitive circuit, it would have been pi by 2. So, let us look at that. So, the first thing that I do here is find out what is the capacitive reactance Xc. That is equal to 1 over omega c. Omega is 1000. and this is 2.5 into 10 to the power minus 4. Now you calculate this, there is already a 10 to the power 3 here, and it works out to 4. Resistance has been given to be 3 ohms. So my impedance, which is equal to R square plus only XC I have got, so XC square. So it is 3 square plus 4 square square root, which is equal to 5 ohms. Now that immediately tells me that my maximum current would be maximum voltage divided by Z, which is just equal to 1 ampere. What about VR max, which is simply equal to IR? I is 1 ampere, R is 3, so it is 3 volts. What is the VC max? Now this is where you must remember, I am not adding. In series resistance circuits, the drops simply added, but I am not adding it, and that would be given by I divided by omega c, IXC. So this is 1 over omega c was 4, so 4 into 1, so that's equal to 4 volts. Once again you realize that I have 3 volts drop across resistance, 4 volts drop across the capacitor, but the total drop is square root of 3 square plus 4 square, which is equal to 5, and let us show it in a diagram. So this is my current direction, that's my VR. Now remember again, I am drawing the voltages. So though current leads the voltage, voltage lags, so hence the negative y-axis. So this is my VC, which is equal to IXC, and if you complete this, you find that that is your supply. And you can easily calculate how much is this angle, phi. This was 3, this is 4, so tan phi is equal to 4 by 3. Let me give an illustration for a circuit which is predominantly inductive. So let's do this. I have a resistance which I take it to be 1 kilo ohms. I have an inductor which I take it to be 4 Henry. I have a capacitor which I take it to be 4 microfarad, and my source voltage is 140 sine 500. That is omega is still 500. I will not repeat the calculation, but you can immediately find out what is XL. XL is omega L. So omega is 500, L is 4 Henry, so it is 2000 ohms. XC is 1 over omega C. Just do the same calculation. This will be 500 ohms. And Z, which is equal to, once again, R square plus XC minus XL whole square, is the simple calculation will give you 1800 ohms. So maximum current is 140 divided by 1800, which is equal to 0.078 amperes. RMS is obtained by dividing by square root of 2, which will work out to be 55 milliamps. Now repeat the same. How much is VR max? You have got IR already. I is this, R you know, and you will get, if you do it correctly, R is 1 kilo ohm, 78 volts. Simple mathematics, arithmetic, I am not doing it. I will simply illustrate the last thing. VC max is I max times Xc, this will turn out to be 39 volts. VL max will work out to 156 volts. So if you calculate the tan phi now, which is equal to Xc minus XL by R, you will get it as minus 56 degrees. The corresponding vector diagram is this. This is your VR. In this case, my VL is bigger. So this is a much bigger one. VC is smaller. So therefore, this is the way I would draw the diagram. And this would be fine. So in other words, you can see the current lags the voltage by 56. So in this lecture, what we have done is to look at a combination of Lcr circuit, and we have defined what are meant by reactances for the inductive and the capacitive elements. We defined impedance, and then we talked about a graphical analysis of the Lcr circuit to determine current, voltage and things like that. In the next lecture, we will be doing a formal analysis which will require the solution of a second order differential equation, but we will sort of take it